Yeah. So yeah, welcome to this presentation. There is still people joining, but yeah. So the goal of this presentation. So that's the sort of first Mind Tech talk. We used to do talks at Mind, but it was only internal, like tech talks that we used to have internally. But here we wanted to start to have something like more wide, where we have more people able to attend these meetings. The goal of the meeting is to talk about technical subjects. So please, if you think about anything, if you have seen something interesting, or read something on anywhere, or you are working on something and you want to share your findings, so please submit a subject, even if you are outside of Mind. We can host the talk, and the goal is to have it regularly, so at least 2 times per month. So that's the intention. We already have some subjects for the next meetings, but if you think about something interesting you want to share, the goal here is not to be like a PhD, to do a PhD presentation or anything. It's really like to share and to have discussion after the presentation. So with that said, we'll start talking about TPM. So what triggered this subject is that at my current mission, my current customer, we are using TPM. So I am using TPM to store secret, protect secrets. And I've seen recently a video talking about BitLocker and bypassing the disk encryption. And so that's really what triggered this presentation, to explain, give a bit of context. So if you have time, you can have a look at this presentation. You will see basically someone sniffing communication on a bus. So you have a TPM, and it is communicating, and basically if you put probes on the board, you can read the secret, so basically get the disk encryption key. But still, the video is really interesting, so I think you can have a look at it. That's also present or give some context about TPM. So what is a TPM? A TPM is a cryptographic coprocessor, so it has different functionalities. So it can generate some numbers, can generate keys, and it can store keys, secrets, data, basically. When we say it can store, it's not like eMMC where you can have gigabytes of data. It's really like small secrets. So generally, you will use it to store article numbers or serial numbers or stuff like that. The TPM is something like standardized. So there is a group called the Trusted Computing Group, I think, TCG, that specifies what is a TPM, what are the functionalities, and then you have vendors like Infineon, for example, that provide chips that implements those specifications. You will see online that there is different versions. The versions currently used is version 2.0. Version 1 is sort of deprecated. I don't know if it's really officially deprecated, but basically you should not use it because the algorithms used are pretty old and not secure anymore. Also, something to know is that a TPM is a passive component. So that's really something, yeah, to keep in mind, is that, yeah, the TPM is not something doing. So we will talk later about measurements. So the TPM is not measuring anything. So basically, TPM receives data, and if you ask it to do something, it will do it. Like if you ask it to sign or to use a certain key to sign something, or you ask it to provide some secret, the TPM will give it, but it's a passive. It's like a drive, basically, but that is able to perform cryptographic actions. So again, yeah, I will come back later on the measurements part. So that's, I forgot to put the source. This is from an image from Wikipedia. That's basically what I just said. I don't know if you see yeah, you see it. So you have a cryptographic processor part where you have yeah, random number generator, you have a RSA key generator. You can also perform some hashes with different algorithms. And you have yeah, an engine to perform some encryption, decryption. And then you have storage, basically, memory. So yeah, the application where it's used, it's mainly used to, yeah, store device identification, like, for example, device certificate or HTTPS certificates. You can store also disk encryption key, etc., etc. Depends the use case, basically, you have. And there is different types of TPM you will see. So there is discrete TPM, we call it discrete. This means that basically your TPM is a chip on your main board or on an external board. So you have your TPM is connected via a bus. And in general, it's LPC, but maybe there is other bus types, I don't know. You have a firmware TPM, so this is part of your CPU firmware. So basically, Intel and AMD has implemented on some CPU firmware TPM. And this is, sorry, basically part of their trusted execution environment. So in this case, basically your TPM is a code running inside your CPU. And you have virtual TPM, so this is provided by virtual machines. Yeah, about implementation, you have multiple options, but the main options you have are two. Feel free to share if you know others. I think there is also an IBM or another implementation, but I think most of the people are using either TPM2 tools or TPM2 TSS. So TPM2 tools is a library. So it's a command line tool that sort of like BusyBox, because I think it's like one executable, but anyway, so that gives you access to all the functionalities that you have, pretty much all the functionalities that you have inside the specification. And you have a library, so there is different level of libraries, sorry, but yeah, the two, so there is FAPI, ES API, and SA API, but yeah, basically, I think everyone uses the highest level one, because even the FAPI is pretty complicated to use, so yeah. And so in practice, what I've seen is that you will use the TPM2 tools for your provisioning. So when you are in production and you want to program your TPM, you will use the command line tools. So that's part of your provisioning script, or call it as you want, or your installer script. And when your system boots and you need access to, or your application needs access to some secrets, you will probably use the library, or the FAPI. So inside the TPM, there is, you will see that they always talk about objects. So objects are general, like, name or entities they give to anything inside the TPM. So a key is an object, an environment area is an object, and this is like addressed sort of by a handle. So a handle is a 32-bit sort of address to your object. And yeah, this object can have different type of attributes, like what it is, like an algorithm, if it's an RSA key, or yeah, symmetric key, or whatever. Another concept inside the TPM is the hierarchy. So hierarchy, they exist, are sort of groups of objects that are linked together. So what it means is that you have a hierarchy. The hierarchy has at its root a seed, and this seed is used to generate everything. So under this hierarchy, so it's like a root seed or a primary seed to derivate the rest. So that's why basically it's called a hierarchy. So for example, if you want to generate a key under that hierarchy, so that key will be basically derived from the root key. In the TPM, you have 4 hierarchies. So there is platform. This is intended for the platform owner, so basically the vendor. I don't think it's used in practice. I'm not sure. We don't use it. You have endorsement and owner. So there you can store like signatures, identities. You can use it for signatures, for your certificates. And owner storage, you can store, yeah, application data, like if you want to store yeah, any data you want, you can use the owner storage also. The null hierarchy is a temporary area. I also haven't used it in practice, so I don't know. Maybe someone in the audience knows, but personally, I've never used it, the null hierarchy. Another concept in so I talked about measurement earlier. Another concept is the PCR. So PCRs are platform configuration registers. So if you have seen like recent presentation from systemd people like Leonard or other guys, they talk a lot about platform configuration registers. So what it is registers that records the platform state. So what does that mean? It means that it's like, again, an object or a memory location where the state of your where you store a value, and that value is specified. So for example, the PCR0 in general contains the hash of your BIOS and your or your bootloader or your early boot. So we will see later. I will explain that, give some example later. So this is specified, and that's how this gives you the platform state. So basically, if you boot, every step of your boot will be hashed and added to that register. So at the end of your boot process, you can, by looking at those registers and looking at the value you have inside those registers, you can see if you have the expected value or not. So, and we, in the TPM language or the TPM vocabulary, we don't say, I mean, it's called an extension. So you don't really like set a value, you extend the value. So it's never possible to set, so if you have a specific hash, there is no way to set it to there is no way, I know. Maybe there is a hacky way, or I don't know, maybe hackers are able to do that. But by specification, it's always like you have the new value that we get is a combination of the old value, the hash is the hash of the combination of your previous value and the newest value you provided happened. So yeah. If you give like a set of zeros or a set of data, any data, it's very complicated to guess what is the value you will have after that. I mean, it's very complicated to get the PCR value to a value you want. Let's put it that way. So extending basically modifies the value contained in that register. Feel free again to interrupt me if you have any question. The goal is to be interactive. So if there is something that is not clear or you want to add some extra information, feel free to interrupt me. So this is like for the first PCRs, the values that are specified. So this is from the Trusted Computing Group. So this is like for a UFI loader, UFI system, and this is the values that are hashed. So basically you are sort of establishing a kind of chain of trust. It's not really a chain of trust, but you have a vision of what has been loaded inside your system and the hashes that correspond. Yeah, I wanted to say also that this is measure boot. It's called measure boot. So basically, you are measuring every step of the boot chain. So if your bootloader is going to load the kernel is hashed. The kernel, I know systemd, for example, they hash the command line of the kernel and they extend it to a certain PCR. So this is measurement. Secure boot, it's not hashing, it's verifying. So basically, every step of your boot chain from your root of trust will verify the signature of the next step. So it's a bit different. And you can have both if you want. You can do a secure boot and measure boot. It's not... another concept in the TPM is sessions. So you can use sessions to authorize the access of an object. So if you create, for example, a key under a certain hierarchy, if you don't restrict its access, anyone will be able to access that key. So you can protect the access to that key by giving a policy. We call it a policy. And that policy can be a password, a hash mark, or PCR policy, authorized PCR policy, policy sign. There is like a huge list of different way to protect objects, the access to objects. So basically, before being able to use, so if you create a key inside the TPM and you protect it, you will need to comply with the policy to be able to use that key. So if it's a password, basically you need to give the password before being able to use that key to sign anything or to use it to establish a TLS connection or whatever. Also, related or linked to that, you have integrated into the TPM, you have a dictionary protection. So this is a way to protect, like on a repetition attack, where people try to access objects. So every time you fail, basically there is a counter that will start to be incremented, and if it reaches, a certain number that can be configured, you are locked from using the TPM. And the time is also a parameter, so you can set it, but by default, I don't know what are we should have checked before the presentation, but yeah, there is a command called TPM2 dictionary lockout, and you can get the parameters for the lockout time and everything. Do you have any questions? No? So I prepared a small demo. This demo will basically show just some example of a TPM2 a TPM usage. I will show a random number, key generation, the PCRs, and we will use also sessions for and policies for password and policy PCR. And I will then talk about policy signed. So let's stop presenting. Yes. Okay. So I have a small system here that has a TPM. So yeah, what I can do, if you look here, you have plenty of. So this is the TPM tools I was talking about. So there is a lot of. Do you see my screen?
Yes.
Yeah. So you have a lot of. Oops. You have a lot of different functions. The dictionary lockout I was talking about is here, so you can do you can use that to search for to get your parameters. So you can, yeah, very simple, just simply generate random numbers like this. You can ask your TPM to give it in hexadecimal format, and you can also so this is like basic, very basic example. I just forgot to show that. Yeah, I have my TPM. So this is the TPM that is used here. So what I'm going to do here is to define a non-volatile area, for example. So that's a memory area. So I prepared some commands to be fast, but feel free to interrupt me again if you don't understand or you want some complementary informations. I will try to answer them if I know. Oops. Okay. I forgot to. I was doing some testing before. Yeah. So here I created an NV index. That is part of the owner hierarchy, basically. So this is the hierarchy that you have. So, and this is the size. So this is 32. I can, undefine it if you want. What I can do also is to do the same, but protect it with a password. So it's the same TPM2 ng define same address. We'll probably copy paste. It will be easier, it will be faster. Like this. Up. Okay. So here, what I did is that I created the same, in the same index. I recreated that index, but with a special authorized way. And the authorization is a password, and the password is mine. Yeah, very simple. What I can do is, again, generate some random data, put it in a data file. And I would like to write this data into my NVRAM. So what I will do is to do TPM2 NVWrite. Yeah. You provide the address and you provide the password. So what we are going to do is be very funny and use Essentium instead of Mind. And it's not working. And it says DA counter incremented. So basically your system is saying, hey, you failed authentication. You have the wrong password. So my dictionary lockout counter is incremented. So if I use Mind, yeah, it's working. So, and if I read my data back, so like this, and it's not input, but output, and I will quickly data out. Yes. So if you look at the data and look at the data out, oops. Yes, okay. Yeah, it's the same, actually. The size, yeah, the size, I mean, the size is not correct, actually. There is some padding. So keys, you can create keys, as I said. So I will create a key. So as I explained in the hierarchy, you have a root seed. So to create child key, you need to create from the root seed a primary key and then derive all the keys from that root key. Yeah. Yes. We can't hear you, Dimitar. Can you try okay. So this is to create a primary key. again, you have your hierarchy. You can create your primary key. And then from that primary key, is it Dimitar or not? I don't know. You can like derivate child key like this. So that's the way you create keys inside the TPM. So those keys are, I mean, that's how you create or derivate keys. Those keys are not really inside the TPM. They are inside, they are generated by the TPM. So a way to, so if you shut down or your power off your system and you come back, your key are not really stored into the TPM. So to make them persistent, you need to load the key that you just created and like make them persistent. So this is done by TPM to load. So this is the command, and you can do it. Is Dimitar back?
Yeah, I'm here. Not sure
Yeah.
if it works now.
Yeah, we can hear you.
Oh, okay. Well, I just wanted to say for the previous comment where you had the envy
Yes.
operations, it actually gave a warning if you see warn reading full size of the envy index.
Yeah.
Right. And this is because when you did the define, you didn't, like the second time, if you go up, TPM to envy define, the second time when you added the attributes, you didn't specify the size.
Yeah.
So it used the default size, which is 1 kilobyte. Right. And it give, that's why, so it's not padding automatically, it's actually padding, it's actually reading the full size.
I forgot.
Yeah. That's the only thing I wanted to add. Thank you.
Yeah, sorry. It's good comment. It's good comment. Yeah, what I was doing, yeah, TPM to load. So as I said, so maybe you were not here, I was just showing like how to create a primary key. So from the like root seed, and then create a child key from that like primary key. So you have primary seed or root seed, then you generate a root key or primary key, and then from that you can create a child key, and then you have to load that key. So if you look here, you have some files. So this context is basically what represents your key generated by the TPM. So, but to make your key persistent over reboot, you have to make it persistent, and you need to load it into the TPM and ask the TPM to make it persistent. So to do that, you use TPM to load and to. So this is the command, basically. Yeah. So you give the context, you give your public part and private part, and you also again get the context. So this means that your key has been loaded into the TPM, but so this is the context of your key, but the key is not still persistent. So to make it persistent, you need to give an address or a handle where your key will be stored. You need to give a hierarchy, and you need to provide the context. So again, as I said, an object is always associated with a handle. So that's the sort of address where you want to store it, and the hierarchy under which your object or your key will be stored. So to do that, you do this. So this evict control, it's really I'm sorry for the name, it's not me, but it's the way to like, maybe there is an explanation behind evict control, but it's the way to do it. Yeah. So now your key is saved into the TPM. You can like remove it by re-evicting control. I think it's like this, if I remember correctly, and it's evicted again. So basically, it's not persistent anymore. Yeah. To use your keys, then you can just simply use TPM2 sign. Like there is functionality to do TPM2 sign. To just, yeah, of course you need to give an object and yeah, but you can use TPM2 sign to use your key. So about measurements. So I said there was registers. So if you look, you can look at those registers by doing TPM2 PCR read. So this is your PCRs. You can also ask to have just like the SHA-256. So these are the measurements. So yeah, here we are on a special system where you only have from 0 to 7. Yeah, if you boot into so if you have systemd enabled probably and other and measurements enabled, you will probably have some other hashes that will arise or other measurements. So you can use those measurements to protect the access to the secrets. So as I explained, to access like a certain key, you can protect it by the state of your system. So you can say, okay, I will never change the measurement. I will never update my system. I would like to be sure that my keys are accessed only when these measurements are equal to a certain value. So to do that, you will create again your key, but you will need to pass a policy. So that's the policy. Yeah, I will show you the example. It will be way more clear. So in the example I will show you, what I will do is to use the PCR23. And so basically my system will only be able to access the key that is protected by PCR23 if the PCR23 value is equal to 0. So that's an example, of course. So I will read the PCR. So here I will just type some commands and explain what is going on. So here I'm just reading PCR23 and I'm outputting it into a file. So if you look, I have a pcr.bin. Then I need to create my policy. So the policy is the way I am going to protect my secret. So if you look in TPM2, you have different policies. Again, I don't have time to cover it, and I will provide you some sources at the end of the presentation so that you are able to read and maybe find the best solution for that fits your problem. So what we do is that we are going to start a session. So a session is, again, you initiate communication. An authenticated session means that you are going to start a policy. So you start that, then you create your policy. So what I do here is that I create a policy PCR. Again, this is a policy C that will use the PCR. Which PCR? It's PCR 23. The PCR is found in pcr.bin, and the policy is saved into pcr.policy. So if you look now here, I have a pcr.policy. Yeah, what I will do now is that I will create a new key, and I will protect it with my PCR policy. So what you see here is, compared to the previous time, I create a key, but this key, I set a policy with it. So yeah, and you see that you have an authorization policy here. So this means that this key is protected by, so to access this key, I will need to provide to be authorized, and this authorization is given by the state of the PCRs in this case. So I load my key into the TPM, then I just generate some random text. Okay, so yeah, and now I will just simply try to access my key to sign some my text. So what I do is that I start a session, but it's a different type of session. It's a policy session. So this means that during this session, I will have to get authorization to access. So it's a specific session. Again, I generate my PCR. Boom. Yeah. So what is so what I just did is that I did the policy PCR. This has been verified against the pcr.bin that I just provided. And so I got inside this session that I started, which is a policy session, I complied with the policy PCR. So after that, I can use this key to sign this text. So now I have a signature. I can use again the signature is verified. If you look here, sorry. Yeah. So what I'm going to stop the session now. So what I will do is to modify the value of the PCR 23. This is the part that I didn't test it before, but should work, of course. So I created some random hash. So if you look, yeah, some data, and I will extend PCR 23. So if you look at here, so we are really running out of time, and I really wanted to do the discussion. PCR read. Yeah, we have, so I will extend PCR 23, boom. So if I read again, you can see that PCR 23 has been modified. As I said, again, it's not the hash that you have here that appears here. So it's like, I don't know if it's possible really to be able to set an expected value inside a PCR. I don't know. So now if I want to, again, get access to my secret, I will need to comply with the PCR, but it says, yeah, it's not correct. So, yeah. I still have an example. I will go through it via slides, and then we'll have a quick discussion. So I will stop sharing this part of the screen. Feel free again to interrupt me. Dimitar, you have way more knowledge than I on TPM. So if you want to
I just wanted to add, yeah, thank you. So hi there, Dimi from TPM.dev, and I want to thank Arnold and Atanas who invited me here. So you did a great job. You covered so much topics in such a short time. I only wanted to quickly address just a few things that you cannot set directly value to a PCR, as you rightfully said. There simply doesn't exist such a comment. This operation does not exist within the TPM itself, so there's no way to request that. And to deduce what should be the amount of hashes that you extend, what is the order, the sequence, because it matters. That's really why we call it tamper-proofed.
Yeah.
From the fact that it's very, very difficult. But the other thing I wanted to say, that while most people are still here, that I don't know if you, Radhwan, if you used the TC 1101 training course. Do you know about it?
No.
Okay, so that's actually great. So the Trusted Computing Group, which is in charge of the TPM specification, hired me to create a course that's free of charge, with the purpose of enabling more developers to understand how to use the TPM and what it can do. So TC 1101 is available, and it covers pretty much what you covered in 1 hour, but of course it does it in more depth. So I'll just drop the link there. And TC 1102 is going to be released probably next week. So it's public course, it's free of charge. And what you did here is amazing. I had one more comment about the sniffing, the TPM sniffing that you mentioned at the beginning. That's actually a design flaw of BitLocker.
Yeah.
Yeah. So I think
that's part of the discussion.
Okay. I'll wait.
Just quickly, I will go through this in a minute. So here is the code to do a different type of policy. It's a policy sign. So policy sign means that instead of protecting your secrets via a certain value of PCRs, you can protect your secret by a public key. So basically you say, okay, only someone that have the private part of this public key will be able to authenticate. And if you can do that, then I will provide access to this key or to this NVRAM. So you have some examples online. So basically here, in this example, we just generate a key pair. We do the same, but instead of loading it into the TPM directly, we load external. So there is a way into the TPM to generate external key. So you can use OpenSSL to generate key and then load them into a TPM. To generate a policy, you don't use policy PCR, but you use policy signed. And what is really different? What you see here is that when you start your policy session, you will do a first policy signed, and the TPM will give you data. And you have to sign those data and give it back to the TPM. And if the signature is correct, then the TPM will free or authorize you to use the key or the secret, or get access to the NVRAM and the secret that's inside. So that's a different way. For PCRs, this is policy PCR, but you can also do PCR authorization, which is like, instead of having simply the PCR, you have the signature of PCRs. So that's also a different way, but it becomes very complex, and that's not really the intent of this presentation. The goal here was just to give you a little bit of taste and to understand how it works. So as Dimitar said, so if you look at the first video, you will see that people are sniffing the TPM bus, so the communication bus between the TPM and the CPU, so and getting the encryption keys. So in the TPM, there is a way to establish secure connections. So that's encrypted sessions, they call it, or parameter encryption, I think also they call it. I've seen both. So what's this? It means that basically, like for TLS, you are establishing a secure channel between your TPM and your CPU. And like that, you cannot sniff anymore or what the data that is going on the bus. So the PCRs, this is also something I wanted to discuss. You also need to know that at the root of the PCR, so you need to trust the PCR, but there is, like for a chain of trust, you have a root of trust. And for the PCR, it's called CRTM, I think. So it's the core trust, root trust of measurements, I think, something like that. So basically, also the PCRs, you can trust them, but to a certain extent. Do you trust really the root of trust? Is it possible to like replay or like since you are sending hashes to the measurements to the TPM, is it really possible to replay those hashes to get certain PCRs? It's not proven to be done, but that's something to keep in mind. Also, what you see here is on that video is that people are using discrete TPM, but now TPM gets implemented also in trusted environments. So you have a firmware TPM that is part of your CPU, trusted execution environment, and so basically there is no way to like sniff anything when you are exchanging or accessing your secrets. Yeah. Another also thing I wanted to discuss is that your TPM, when you are talking to the TPM, that's why I wanted to present policy sign, because in policy sign, basically your TPM wanted you to authenticate before being able to access the secret. So, and this is possible if you can store a secret. But on x86, for example, there is no way to have a secret, to store a secret. Yeah, like a private key, where are you going to store it? There is no like secure place or secure memory to store a private key. So yeah, that's another thing. So on some other CPU, like I know some colleagues are using Zinc, and they are using these policy signs to like authenticate both sides of like CPU or SOC in this case, and TPM. So to solve that problem, people are using a remote. So instead of doing attestation or authorization locally, they basically, our TPM is sending, or your system need to send, the secret are stored on a server, and so that's the server has the secret, and so is able to provide the access to the secret. That's also used to verify that your TPM is running on a trusted platform. So instead of being just random data like you have seen in policy sign, you can also use a quote. They call it a quote, and that's like some data that represent the states of the PCRs, and you send it to the server, and the server can verify, okay, this measurement has been done, they are correct, so I will authorize this system to run and unlock the access to the secret locally. Yeah. Yes.
Yeah, sorry to interrupt you. I have a very quick question because you addressed during the beginning of your presentation, you mentioned, sorry, for FTPM, you mentioned AMD and Intel, sorry. Do you know or have you experience with other architecture like ARM? Because I know, for instance, in the context of Opti, there is some trusted application of an FTPM. But I also remember from what I remember, which is maybe not up to date, that it's not actively maintained and there was no support from ARM64. Do you yourself have experience of ARM architecture with in the context of NFTPM? Sorry.
FTPM, no, I haven't worked with that. So as I said, we have in our team we have a Zinc. So that's an ARM. There is an ARM CPU there, but it's we are using like a discrete TPM and not a firmware TPM.
Okay.
But yeah, I mean, I don't see why there will be any difference actually. But yes, Charles-Antoine. Yeah, or Paul-Henri, maybe you wanted to add something.
No, just saying it's not about the difference. It's more about, if you would have been aware, for instance, it was a really specific question about Opti and FTPM support, because it's just to know if you would have had more recent feedback, because I remember that it was not really actively maintained and such things. So I was just curious.
So my question is integration of the TPM in the different tools related to security, like Lux for the encryption of the disk, or OpenSSL, as you mentioned. Apparently, we have to play a bit with the commands from TPM, but do we have the possibility, for example, to ask to OpenSSL, okay, I want to generate these keys, store them in the TPM, and then the next request, I can just ask this task to OpenSSL, which is doing the right TPM commands for signature, etc. Or do we still have to play with the TPM command?
So in OpenSSL, you have something called engines. So you can there is examples. So here on the TPM2 software repo, this is not, so there is a lot of repository under that. And you have an example of OpenSSL TPM engine. So what you need to do is to use that engine. And so OpenSSL, instead of running on your CPU, will use the TPM to perform your cryptographic actions you want, so like signing and everything. So does that answer your question, Charles-Antoine?
Yes, and do you know if it's available also for Lux, for example, to encrypt and decrypt the disk?
So I attended LPC, and apparently since recently they support so the keyring of the kernel supports TPM with parameter encryption now. So you can also load keys from the TPM and use the keyring to do that. Yeah. What you can do also very simply, if it's just for decryption, is just you perform your actions, let's say, or your commands to get access to your secret, and then pass it to Lux or to Crypt Setup, and that's it. If you have your encrypted sessions, your secrets are not transition. I mean, they are not available in plain text.
Okay, thanks.
Olivier. Yes, and after Dimitar.
Let Olivier go first. He was first.
Yeah, Olivier. We can't hear you, Olivier.
And now, do you hear
Yes.
me? Okay, sorry. To answer Paul-Henri, the traditional, as far as I understand, the traditional way to have the same security with the ARM64 is with a secure element. That's what we use at Fort Robotics, my current customer. I shouldn't have the customer, sorry. But we are busy with a system that has implemented quite a lot of security. And it looks like it is really the standard solution for smartphones, having a secure element inside, which is basically implementing the same things as a discrete TPM, but the standards are different. That's it. And so I am also aware, but top of my mind, of a TPM implementation in Opti, so that you can actually use the hardware of secure element, but the APIs of a TPM, if you like. And it's probably more directed to ARM64 in the cloud and things like that.
Okay. Okay, thank you.
And my small question is, how fast is it? It looks pretty slow.
A TPM? Yeah, well, I think it's slow by design. I think the goal is not, so if you want to decrypt huge amount of data, you should not use a TPM. That's not the use case. Basically, you store some secrets and you give access, so you verify signature, you do some established TLS connection between your IoT device or your small, I don't know what is your target you are working on, and a remote server. So that's more the use case than like having something super fast.
Okay, thanks.
Dimitar.
Hey, yeah, thanks. So again, amazing that you managed to fit all that knowledge in 1 hour. Like, for real. Kudos for that. And I just wanted to share my experience. So former TPM has been used on ARM, even with ARM v7 way back. You just get the TPM simulators or the TPM reference implementation. The one is from Microsoft, the other is from IBM. It pretty much shares the same code. And then there's one other former TPM from Stefan Berger, which is usually used in the cloud as a virtual TPM. And that's the fun story that back in the day, maybe 4 years ago, virtual TPMs were actually virtualized, discrete TPMs. Like there's actual hardware. Nowadays, almost no one does it. A virtual TPM is just software. So it's a very different security guarantee. Now, today, what I'm seeing is a very high trend of adding TPMs on embedded systems, especially ARMv8, ARM64. It's not just discrete TPMs. You have 4-core Cortex-A. One of the cores becomes a dedicated trust execution environment or becomes its own whatever, like firmware that actually has a single purpose to be the secure enclave that runs a firmware TPM. And you can do the same probably with OptE, but you would have to probably do most of it yourself. I do not agree that using secure element is the same as using a TPM. The major difference, okay, is exactly the policy that Radhwan showed. Like you don't have PCRs on a secure element. There's one exception, and that's the NXP SE050, which uses a Java applet to emulate a TPM PCR. So there's a big difference. What secure elements are best at are providing you modern curves and algorithms, because the TPM is very slow, because standardization takes a lot of time. So I just wanted to share about the question about speed. This is one of the lectures in the course that talks about when not to use a TPM, and it gives examples and stuff like that. So it's very interesting to see Mind and Radhwan and so many, like 5 folks joined with questions about TPM or use cases. It's very nice to see that there's a trend of adoption happening, that it's being used, or you try to use the TPM, okay, it's too much, or it's too slow, or hey, we need a more modern curve, so we go to a secure element or we go to a firmware TPM. But it's really nice. Thank you for having me.
You're welcome. We are happy that you were able to join. Any other questions? Yeah. If not, then I think we can stop. I will stop the recording. Okay.